Okay, we're going to talk about how to solve equations that have logs or exponentials in them. And the problems you'll see won't be this basic, but I want to give you the basic principles and fundamentals for how to do this. You may have to do other operations to get an equation to look like the one that you see here. But the idea is once you have an exponential isolated on one side of the equation, I'm going to give you the techniques to solve it. So to solve an exponential equation, I need to get the variable out of the exponent. To do that, you're going to use properties of logarithms. So you're going to have to take a logarithm of both sides of this equation. Any log is going to do. Okay, you can use any logarithm, any base you want. But since we're mostly tied to the natural logarithm, based on uses of a calculator and using calculus in the future, I want you to get used to using that logarithm. So my first step is to take the natural logarithm of both sides. It looks like this. Natural log of 3 to the x plus 2 equals the natural log of 7. Okay, and I want you to be very clear. We're not multiplying both sides by ln, even though that's maybe what it looks like to you. Okay, we are making both sides of the equation the input of a natural logarithm. Okay, very important. Now, what does this do for me? Well, I have a property of logarithms that says when I have log of something to a power, the power is allowed to come down in front. So in this case, the power, which is x plus 2, may come down in front of the logarithm, which is now the logarithm, natural logarithm of 3. The other thing we have to understand is that log 7, or in this case ln7 and ln3, are numbers. They're constants. So even though they're not numbers we're used to looking at and dealing with, they are still numbers. Okay, so now my job is to solve for x to isolate x. And that's easy enough to do. I can divide both sides by the natural log of 3. And then I can subtract 2 from both sides. And so if I have a calculator, I can get a decimal approximation for this number. Otherwise, I just leave it as it is, and it's in its perfect form. Okay, now I have a logarithm inside or in an equation. And again, you may have to do other operations here to get the logarithm isolated. But once you have a log isolated, the operation that gets you, or I should say that cancels out the logarithm, okay, is to what's called exponentiate both sides. Okay, what it means is you're going to take and make both sides the exponent on some number. Now, since I have log base 2, it makes sense to make 2 the base that I'm going to make these two sides of the equation the exponent for. So here's what it looks like. 2 to the log base 2 of x plus 2 equals 2 to the 5th. All right, the right side's easy enough. That just becomes 32. And the idea here is, again, using properties of logarithms that says 2 to the log base 2 of stuff just becomes stuff. In other words, this part here cancels out. So conveniently enough, you're left with x plus 2 is equal to 32, and so x equals 30. Now, let me just show you maybe an alternative way to look at that may be easier for you. Kind of gets you away from this verb exponentiate, but really that's what you are doing. But if you rewrote this log 2 x plus 2 equals 5 equation in exponential notation, it would be 2 to the 5th equals x plus 2. And that's just using basically what a logarithm means. It means 2 to this power equals this. All right, but really you're using this verb called exponentiating. Let me do one more example here, because sometimes you may have an equation that has 2 logs in it. So you can't just isolate the log and go from there. So here you have 2 different logs with the same base. And I'm going to show you 2 approaches to handle this. All right. One approach is to say I'm going to exponentiate both sides right now. Okay. So if I do that, I would use, in this case, 10 as the base. So I'd have log x plus log of x minus 3. That's all the exponent on 10, because I exponentiate the whole side, not just the pieces of the side. Now on the right side, I would have 10 to the first. Now I have to be very careful. What can I do with 10 to the log x plus log of x minus 3? Okay, well, I know that if I have a number and I'm adding exponents, that came from multiplying 2 things with the same base. That's when you add exponents, okay? So this can be rewritten, this left side, as 10 to the log x not plus, as many people want to do, but times 10 to the log x minus 3. Now I can use my properties of logs and exponentials. I know that 10 and log 10 will cancel, so I have an x times, again over here, 10 and the log 10 cancel, and I have an x minus 3 equals 10. Okay, now from there, I can't just say that means x equals 10 or x equals 13. That's very bad and a common mistake that we see. And we're going to make one side equal 0, and we're going to try to factor the number 0. So hopefully this factors, and I think x minus 5 and x plus 2 will do it. So my solutions on paper are x equals 5 and x equals negative 2. I should always go back and check that these numbers work in the original equation. And if I go back and look, I'll see that I cannot plug in a negative 2 into log x because that would give me a negative number inside of a log. So this answer here is extraneous. All right, let me shrink all this down real quick. And let me show you maybe another way to do this that you may like better. Okay, I can, from the beginning, instead of exponentiating first, I can combine these two logs into one log because I have a property that says the log of a product becomes the sum of logs, which means that a sum of logs becomes the log of a product. That would give me log of x times x minus 3 equals 1. And now I can do the exponentiating at this stage. So I have 10 to the log of x times x minus 3 equals 10 to the first. 10 and log 10 will cancel when they're in this position. So now I have x times x minus 3 equals 10. And I'm in the same position I just was, where I can just now solve for x and double check for extraneous solutions.